Hello, everyone, and thank you for joining us today. We really appreciate your jumping in, and we'll be eagerly presenting a discussion, an overview of the compliance verification measurements that are specified in TR53. Arnie will be the presenter, and Ginger and I will interrupt whenever we feel like it, but generally Arnie is driving the ship. And as just a housekeeping matter, if you're welcome to talk anytime, ask us questions, or you can use the chat box if you prefer to do it that way. Either way is fine. And we will address the questions as best we can along the way, and perhaps at the end if need be. So I know most of you are familiar with us and my team, so I won't go into that in much depth, but for those who might not be as familiar, I wanted to point out that we have a team of great people, number one, and experts in a very broad range of areas, including manufacturing issues, dealing with extreme sensitivities, and also in terms of product design, in design hardening for especially circuit boards and systems. So we have the full range of expertise, and we do not sell any products, as you can see on the first slide here. Now, as you can see, we've had interesting engagements all over the world. In the interest of time, I'm not going to get into that in depth, but I can just tell you that Ginger had a wonderful time in Alaska in the winter. And we had just missed a cold spell of minus 47 degrees. And with that, Arnie, let's go to the next slide. We do have an upcoming training opportunity in about 2 weeks. This is, in fact, it's the certification version of what we're going to share today. So it's much more in detail than time will permit today. It's a 3-day classroom activity, actually 3 half days. It's half days. And then on the following 2 days, we schedule a 1-hour practical exam for those who want to be certified. And that would be on Thursday and Friday. And we can accommodate everybody's individual schedules the best we can. And that is also virtual. And we include TR53, which you may know is primarily a human body model document. And we add to that the charge device model, a charge board event, and cable discharge, so that it's more comprehensive than just the standard TR53 certification course. So you'd be in a great way to go forward with that after the training. And you should be receiving notices. If not, let us know and we'll be glad to share that, or you can find it on our website. Also on our website are a series of complimentary short training videos. The basic fundamentals. I'd encourage you to go there and look at them, and look at also some of the free recorded webinars online. With that, I want to just introduce Arnie, which is a pleasure. He is a great friend and valuable, invaluable member of our team. Most of you know him as the ionization expert. He's written the association, the initial version of the ionization standards, and has designed many of the ionizers that are available today. Today, of course, he's going to show his expertise in the TR53 certification training. And again, it's an overview today, and the detailed training is October 18th, the week of October 18th. So with that, Arnie, I'm going to turn it over to you. And
hey, Ted. Thank you. Thank you.
You're welcome.
For that nice introduction.
Oh, my pleasure.
Okay, let's see if I can get this working. Okay. Okay, so this is kind of a, sorry you're getting this other thing on top there. I can't get rid of it. It comes back all the time. We're going to talk about TR53 measurements today. We're not going to talk about troubleshooting. That would be covered in the longer TR53 course. What you have here in white are the items we are going to cover, and some of the other things that are in the orange color are the things we won't cover today. So the numbers to the left are the numbers of the actual sections in TR53. So if you have TR53, you can follow along. And when you get TR53, these are the sections that you will be seeing. So this is part of the partial list of what's in TR53. And here you have the rest of the list that's in TR53. And once again, we'll only be covering the issues that I've highlighted in white here. So to perform the TR53 measurements, you need a kit of instruments. And I've got what I've listed here are the things that you would normally need in your measurement kit to handle all of the issues for making TR53 auditing measurements. If you don't have a particular static control method, like if you didn't have an ionizer in your facility for some reason, you wouldn't need the instruments that would be used to check the ionizer. But in general, this is the list of instruments that you would need if you wanted to do your auditing of a full static control program. And we'll talk about these individually as we go through the material this morning. So what's the first thing you do? Well, you wake up in the morning, you go to work, and you get out your instrument kit, and the first thing you need to do is verify the instruments. You want to do some testing to make sure that all of your instruments are performing the way you expect them to perform. So what you're going to do in each case is follow the manufacturer's operating instructions to verify that the test equipment is operating properly. And each instrument will have its own verification procedure. In the auditing process, most of your instruments will be battery operated, so you should always, before you go out into the factory to make measurements, check all the batteries. It's a very good likelihood that within a day of doing testing that one or more of your instruments is going to need to have its batteries replaced. So pay attention to the battery indicators on the instruments. And make sure that before you start the day with a full set of new unused batteries in your instruments, because otherwise you're going to have to be changing them very often during the day. So an example here, the resistance meter verification, you put the two 5-pound weights on a metal plate so that you're essentially shorting them together, and you measure the resistance of through the two electrodes. As you can tell here, the measurement is about 390 ohms. That's a typical measurement that you might see. We typically are looking for a resistance of less than 1,000 ohms going through the two electrodes. So now the first thing we're going to look at when we go out into the factory is the grounding system. We need a good grounding system to be able to make most of our ESD control measurements. So the first thing we're going to do is verify both the AC power and the grounding system wiring. You want to make sure that the AC power wiring is correct, and you want to verify that the grounding system for ESD is properly wired. Your references here are for ANSI ESD S6.1 grounding and the National Electrical Code. So here's a table of our grounding bonding systems. This is the table from S2020. Where we are looking for our equipment grounding conductor. That is the preferred grounding method, and that's detailed in ANSI ESD S6.1, and the requirement is that the grounding system have less than 1 ohm impedance. That is the requirement for your ESD grounding system. The other 2 grounding methods we're not discussing here have to do with what you do when you can't use the equipment grounding conductor as your ground point. So there are alternative methods, but we won't cover them here. So once you have your instrument, this is your AC circuit tester, you plug it in to the receptacle that you're going to use for grounding. And as you can see, you have 4 tests here. First of all, we want to verify that the neutral and ground wires are not connected at the receptacle. We want to verify that the AC high and AC low or neutral are not reversed. We want to verify that AC high and the ground wires are not reversed. That would be very dangerous. In any case, what you see here is 2 testers that are used to make these measurements. One of them has other methods that other tests it'll perform, and the one at the bottom is a very simple one that just checks the wiring and actually provides you with a ground connection so that you can access the ground at that socket. So this is what we would do first, make sure the wiring is correct. Then we would verify that the impedance of the ground line. Now you do that with the upper tester that you see here. That has a position where it will test the resistance of the hot, neutral, and ground lines. Now, one thing as a caution here, that if you check the impedance of the ground line with this tester and you have a ground fault interrupter on that line, it will set off the ground fault interrupter. So, and that can have significant effects in a factory where, it might shut down a lot of equipment. So when you're doing the testing of the impedances, unless you are absolutely sure there is no ground fault interrupter on the line, don't test it. If your hot line and your neutral line are both measuring under 1 ohm, there's a very good chance that you can assume that your ground line is below 1 ohm as well. It's unfortunate that with a ground fault interrupter on the line, you can't do the test. As I understand it, S2020 will be modified in its next version to allow for not testing this ground impedance. Okay, here's a picture of what your grounding looks like. This is the typical way that we do our grounding. You have your equipment ground. That's the 3rd wire in the receptacle, the green wire. You connect that to your common point ground. And then you want to make sure that the resistance from your common point ground to your equipment ground is less than 1 ohm. So that's the next thing you will be measuring. You're going to measure the resistance from the common point ground to your AC ground and make sure that that's less than 1 ohm. Here's an example of what a common point ground would look like. What you see here is a terminal strip with all the terminals wired together. On the left, you have the green-yellow wire, which is connected to the actual ground. And then you see another green wire here. This might be a mat ground. It might be some other ground that you need to have at your workstation. Typically, you'll have a ground for your wrist strap system connected here. You might have a floor, a table mat ground connected here. You might have a floor mat ground connected here. The reason we use the common point ground is so that someone doing the auditing can see very quickly if all the required wires are connected to this common point ground. The alternative for an auditor is literally crawling around on the floor trying to trace where all the wires go. So we strongly recommend in any setup of an ESD control program that you put a common point ground on each workstation and connect the wires to it, because otherwise the auditor's job gets to be very nasty. So our common point ground is connected to our equipment ground, or if there's an auxiliary ground, we connect it to the auxiliary ground. We connect the wrist strap connector to that common point ground. We connect the workstation work surface to that common point ground. We have, if there's a protective mat on the work surface, we connect that to the common point ground. And if we're using any kind of floor mats, we will connect those to the common point ground. So what you've seen here is that every element of your workstation has been connected to this common point ground. And all the resistance of the wrist strap connector, from this wrist strap connector to the common point ground to the equipment ground, that needs to be less than 2 ohms. Every wire in here, each individual wire, needs to be less than 1 ohm. So for the wrist strap connector, you have 2 wires to the equipment ground. So that's why the 2 ohm resistance is the pass value. But for all the other wires, they are measured to the common point ground. So you have 1 wire, it should measure less than 1 ohm. Test procedure, very simple. Connect test leads to a DCO meter, connect 1 test lead to the personnel groundable point, and connect the other test lead to your AC ground reference, and the S2020 pass value shall be less than 2 ohms for each test point. Very simple measurement. Now for work surfaces, we want to verify that our ESD work surface is electrically bonded to the ground reference. Now, we want to check this because we have seen many times that if the wire from the work surface to the common point ground is not there, it is still possible for that work surface to pass its 10 to the 9th ohms limit, but it's not reliable. So we want to make sure that we have work surfaces that meet our resistance requirements, and also we need to check them to make sure that they are indeed physically grounded. You can use this test method on shelves, drawers, and any kind of ESD protective storage equipment. Our references you see here, standards from the ESD Association that give you the information you need to measure these work surfaces. Now, let's talk about the measuring equipment. Standards specify that if the resistance range you're measuring is less than 10 to the 6th ohms, that the test voltage will be 10 volts, and your electrification period, how long you wait before the measurement stabilizes, is 5 seconds. Now, if your resistance range is 10 to the 6 ohms or greater, then the standards specify that the test voltage should be 100 volts. And then you might wait as long as 15 seconds for the measurement to stabilize. Now, some instruments, you have to switch them. You make your measurement at 10 volts. If it's above 10 to the 6th ohms, you switch to 100 volts. Other measuring instruments will do this automatically for you. They will sense what the resistance value is and choose the proper test voltage. So depends on the instrument you have, whether you do this manually or it's automatic. You're going to have to verify this resistance test equipment, make sure that it's working correctly. You want to examine your electrodes for dirt buildup. Sometimes if you have to use them, especially if you're making floor measurements, they will get dirty. You need to clean them. Usually there's some kind of cleaning solution or using IPA, but whatever you use, always allow the electrode to dry before you retest it. Here's a picture of those electrodes. They're nominally 5 pounds or 2-point-something kilograms, and diameters 2.5 inches. And there's an electrically conductive rubber on the bottom. And generally, when we measure the resistance between the 2 electrodes, we put them on a metallic surface, the measurement should come in usually under 10 to the 3rd ohms. So What does our measurement look like? Well, for TR53, the important measurement is the point to ground resistance of the work surface, or RTG, resistance to ground. It's used for compliance verification. You're going to use it if you do troubleshooting, and you'll use it for, doing more detailed analysis. This is the main resistance measurement you have to make. We've seen many times in ESD control programs that they also specify a point-to-point measurement on the work surfaces, but that's not required by TR53. You usually only make the point-to-point measurement when there's some problem that you've identified with your point-to-ground resistance measurement. So your equipment that you need to make this measurement: a high resistance meter, 1 electrode, 2 test leads, and some type of ground adapter plug so that you can connect to the AC ground. Which you see in this picture here, you see the meter, you see 1, 2 test leads, you see the 1 electrode on the work surface, and you see the ground adapter plug with the ground lead from the meter plugged into it in the picture. So what do? Well, we attach the leads to the meter and the electrode. We attach the leads to the meter and the common point ground. We place the electrode at appropriate locations on the work surface. Usually look for worn or damaged areas of the work surface. You want to test those first. You want to apply either a 10 or 100 volt test voltage based on resistance. You want to record the data after 5 or 15 seconds, depending on the resistance. And the S2020 pass value shall be less than 1 × 10⁹ ohms for each test point. And I think, Ted, you've got a demo set up on this?
I do. I'm going to take the sharing over for a moment. Let me go. And let me go here. Okay, are you seeing my desktop?
I think we see it.
You see
Yes.
you see the meter?
Yep.
Yes.
When I said desktop, I really mean my service. Okay, so what we're going to demonstrate is what Arnie just suggested, and also this is also an illustration of the way we do the certification training. And I'm going to actually, Arnie or Ginger, either one, maybe you could kind of step me through this and tell me how to make this resistance to ground measurement.
Well, you've got an electrode there. It needs to be attached to the instrument. And based on what Arnie has said, I'm assuming you've already verified that the instrument worked.
Yes, I did. Okay, so how do you want me to do it?
Well, you plug one lead into the 5-pound or 2.27 kilogram weight, and then plug another one into ground. Probably be good to go straight into ground over there, or your common point ground, but and turn the meter on, make sure it's calibrated. Okay, so this particular meter does a self-check, and it said it was good. Or maybe it's just giving Ted a positive affirmation.
There you go. And
So I think you should push the test button, the green one.
right. Ginger likes this because she gets to give me orders and I have to follow through.
Well, this is partly how we do some of our training, by having the students walk us through it so we know that they know what we're supposed to do. It's a little difficult to do this remotely, but by having individual students tell us, we know that they are paying attention and can do the measurement. And so Ted becomes sort of a directable robot. And so the result here is 2.1 times 10 to the 6th. So can anyone in the audience tell me if that is a pass based on what Arnie has told you so far?
Yes, it is a pass.
Excellent. Great. I see a little thumbs up too. Also, Arnie, there is a question from Gary in the chat. He was wondering, what's the purpose of starting at 10 volts if you get a fail and then you just have to retest at 100? Why don't you just test everything at 100?
Well, I guess the reason for not testing 100 first is always that you don't want to, connect 100 volts to a low impedance circuit. It wouldn't damage anything, it would just load it down, but it's probably not, the best thing to do for your equipment. It's always better to start low, verify that your resistance is greater than 1 mega ohm, and then switch to the 100 volts.
And Gary, from what I understand is there were some materials, I'm not sure we have them anymore, but if they were tested at a higher voltage and they were quite conductive, it might actually damage the materials, burn little pathways through the material, so you wouldn't be getting a true reading. And so that's another reason to start low until you know what you're measuring.
All right, thank you.
And then Pascal was asking if a minimum resistance is a minimum resistance not recommended. It is recommended in a best practices situation, but it is not called out in 2020 or TR53. So you are very smart to be sensitive to that. Obviously, you don't want to put a sensitive device on a hard ground if it might be charged up. So that's a very good question. And we recommend that you do think about adding a minimum resistance in your facility.
Yeah, that's one of the things that we'll cover in some detail in the certification course and in others.
So I think Arnie's trying to get the slides back. Or are you done, Ted, out there?
I'm finished, so Arnie's ready to roll.
Okay, thank you, Ted. There we go. Okay, so after we've done the work surfaces, we need to check the wrist straps. Now, checking wrist straps is something that you would do every day. It's a way to verify that the wrist strap is working correctly. Though I have to say that most ESD control programs today, rather than depending upon people doing individual measurements of their wrist straps every day, have found that if you use constant monitors on the work surfaces, that's a much better way to assure that the wrist straps are working. But what I'm going to assume at this point is that you are doing wrist strap checking by some means. So here you have two methods used for testing wrist straps. One of them is an actual wrist strap checker. You put the wrist strap on, you plug it into the checker, you press the button on the wrist strap checker, and you basically make a measurement, and it says either high, pass, or low, depending upon the resistance you measured. You can also do the same thing with just a resistance meter. What you see is the person has the wrist strap on one hand, it's connected to the meter, and they're holding the electrode in their other hand. So what they're doing is they're measuring from the electrode through the wrist strap to the person's hand, and they're getting a measurement of the wrist strap that way. The S2020 pass value, you have to be less than 3.5 times 10 to the 7th ohms, but in most cases, your wrist strap is going to test around 1 mega ohm because that's what the resistor in the wrist strap is. But in any case, the maximum allowable pass value for S2020 is 3.5 times 10 to the 7th ohms. Now, the other way of grounding people is through footwear and flooring. So we want to check the footwear. We want to verify the resistance of the footwear system, both the person with the person and the footwear. We want to make sure that it meets the specified minimum and maximum resistance range. Now, footwear can include ESD shoes. It could be heel grounders, could be sole grounders, could be booties. There's a wide variety of footwear that's available out there, and you want to check it with the person to make sure that it meets your resistance requirements. So the most common way this is done is with an integrated tester. You basically step on the foot plate, you activate the tester, and the tester will check the footwear. Some testers will also check wrist straps at the same time. You wait for a pass indication, and if there's a failure, you perform troubleshooting. One of the common things that people do with these integrated footwear testers is connect them to the door into the work area, so that unless you pass your footwear and in some cases your wrist strap test as well, you don't get to go into the work area. You have to fix the problem. So this is a very common way of making sure that people's wrist straps and footwear are indeed working, because if they don't pass this test, they don't get to go into the room. So how do we make these measurements? Well, this is a list of the methodology for making a measurement using just a resistance meter. You wear the ESD footwear according to your company procedure. You connect the test leads between the handheld electrode and the foot electrode to the meter. And you hold the electrode in one hand and place one foot on the other foot electrode. You do have to stand on one foot to make this measurement, or you have to make sure that there's something else that the person can put their foot on that isn't conductive and is on the existing flooring. So basically, you're measuring between the person's hand and the bottom of their shoe, and you want the resistance here to be less than 10 to the 9th ohms. According to S2020. So this is another way of making that footwear resistance measurement and verifying that the footwear is indeed working. Now, footwear has to work with flooring, and we have to check the flooring system. The floor may consist of a permanently installed floor, could be several different kinds of materials, or it could be a floor mat. It could be a floor that its ESD properties depend upon a floor finish, a coating, or a paint. ANSI ESDS 7.1 is the reference here. And the measurement methods and the troubleshooting are similar to the work surface measurements. You do the same resistance to ground measurement, and if you need to, you do point-to-point measurements on the floor. Now, many ESD control programs use ionizers. They're principally there to control the charge on insulators and isolated conductors, make sure that they are held to very safe levels. And there are methodologies in the ESC standards, both STM 3.1, that's not SIM, that's STM 3.1, and then SP 3.3 is the document that's called Periodic Verification of Air Ionizers, and it contains the procedures that are used in TR53. So what you're going to do is to follow the SP 3.3 test procedures for room ionization systems, for laminar flow hood ionizers, for work surfaces and automated equipment, both benchtop and overhead blowers, and for compressed gas ionizers, guns or nozzles. Those test procedures are in SP 3.3, and depending upon which ionizer you have, you'll use one of these procedures as part of their TR53 auditing. The equipment for measuring ionization systems as specified in the standard is called the charge plate monitor, or CPM. There's the full-size CPM that has, an instrument and its associated plate unit. You see that on the left on the bottom. Or you can have a portable charge plate monitor, which consists of a field meter and a plate assembly with a timer, could be an integrated timer or a stopwatch, and some type of charging device to charge the plate. So this is a portable unit. It's the most likely one you'll use during an audit. So you will have these instruments available to you. And the methodology is also specified in TR53 for making the measurements. So what you see here is our setup for our decay time measurement. We're placing the charge plate approximately 12 inches downstream facing the ionizer, or you can place it where your product is processed. and just record the location so that you can go back to that same location to do verification in the future. So either pick a distance from your ionizer or pick a location based on your process. Either one is fine for TR53 measurements. So first, you're going to momentarily ground the plate and verify that 0 DC, it's been adjusted for that. Then you're going to charge the test plate over 1,000 volts. The plate will decay because of the ionizer, and when it reaches 1,000 volts, you start the timer. You run the timer until the voltage on the plate has been reduced to 100 volts by the ionization. And then what you have now is the time from 1,000 volts to 100 volts. That's your discharge time measurement. And you want to verify that it meets the facility spec. There is no standard that tells you what the ionizer should do. It's always based on your process. So you have to decide what you want your ionizer to perform at, how fast the discharge time needs to be, and you need to verify periodically during your audit that your ionizer meeting that specification. So first you do it for positive 1,000 volts, and then you repeat the testing for minus 1,000 volts to make sure that your ionizer is working for both polarities. Now, the other measurement for the ionization system is the offset or balance measurement. This is specified in S2020, and the requirement in S2020 is that the balance must be less than plus or minus 35 volts. So to make this measurement, you place the isolated plate approximately 12 inches downstream facing the ionizer or where your product is processed. You've already decided where you want to make that measurement, so you make the balance measurement in the same place you made your decay time measurement. Record the location for future verification, and then momentarily ground the plate and verify that you've got 0 volts DC on the plate. Then wait the manufacturer's specified time. Usually it's around a minute, maybe for room systems, you might wait as long as 4 or 5 minutes. But whatever the manufacturer's specified time is, wait that time, and at the end of that time, you're going to record the offset voltage that you saw on your meter. That the S2020 pass value, as I said, less than 35 volts at each test point for both polarities. So plus or minus 35 volt maximum. Okay, now let's look at their mobile equipment. What you want to do is verify that your resistance to ground through the grounded floor of your mobile equipment meets your specifications. Or you might have to test mobile equipment with a ground cord. Some factories use mobile equipment, but they don't have a conductive or dissipative floor, so they must use a ground cord when the mobile equipment comes up to a place where it can be connected to ground. Your references are listed there: 6.1 grounding, 53.1 ESD protective workstations, and S4.1 work surface. Measurement technique, much the same as work surfaces. So what you're going to do is place the mobile equipment on its the grounded floor. You don't clean it prior to verification. You always want to see how it's working in place. You're going to remove all the ESD sensitive items from the mobile equipment because your meter does put a voltage on it. You want to make sure that there's no possibility of damaging the equipment. The same thing is true when you're making workstation measurements. You want to make sure that there are no sensitive items left on the work surface during the testing. You're going to connect the ground adapter to your AC electrical outlet and connect one of the meter leads to that. You're going to connect the meter to the ground adapter and our test electrode here. You see it on the shelf. You position the electrode on the top shelf of the cart first. You want it as far away from ground as you get it, and you want to make sure that the pass value of 1 times 10 to the 9th ohms is there at every point you check. After you check the top shelf, you want to check the middle shelf. After you check the middle shelf, you want to check the bottom shelf, because there's no guarantee that given any one shelf is connected to ground, that all the rest of the shelves are also connected to ground. You see in the picture here a drag chain, little tiny drag chain. We don't recommend using these. They make very unreliable contact with the floor. You really want to be using dissipative or conductive wheels on your cart as your grounding method to the floor. Drag chains almost always fail. Okay, so moving on to packaging. Your objective here is to make sure that your protective packaging that you're using in your process is meeting your resistance requirements. The ESD protective packaging could be waffle packs, it could be bags, it could be totes, bins, and storage boxes. There's lots of different kinds of packaging material. Some packaging material is meant to be used within your EPA, your electrostatic protective area. Other packaging material is meant to leave the EPA and be transported in the rest of the world, essentially. So it may have different requirements than packaging that's just used in your EPA. You see your references here to the main packaging document, S541. S8.1 is the symbols document that tells you how to mark the packaging. And the other three standards, 1111, 1112, and 1113, are your surface and volume resistance measurement documents. So here's some pictures of what the packaging test might look like. You always put your packaging sample on an insulative support surface, many different kinds of meters. Some of them have electrodes integrated with them, so you place them down on the surface on top of the packaging material, and you make a measurement. Another way to make the measurement is what we call a concentric ring electrode. I have a picture of that I'll show you in a minute, but this is another electrode that has been designed to make measurements on packaging materials. There's a 2-point probe. We use the 2-point probe when we have material that's not flat, that we can't put our other types of electrodes on. This is a 2-point probe, especially for things like JEDEC trays, where you have pockets and you want to make measurements in those pockets. The 2-point probe will make those measurements. And then, we have a drawing on the bottom of our favorite 5-pound test probes, which also can be used for measuring the packaging material. Here you have a picture of your concentric ring assembly. This is an electrode that's described in STM 11.11. Consists of 2 concentric rings made of conductive material. The inner electrode is a solid disc. The outer electrode shall be a ring, and the total weight shall be 2.27 kilograms or 5 pounds. And what you're measuring is the resistance between the inner and the outer electrodes. And the size of those electrodes has been calibrated to give you a resistance measurement in ohms. Here's a picture, a close-up of our 2-point probe. You see the 2 electrodes. Some of the 2-point probes will have a conductive rubber on the bottom. Others will have just metal to make the contacts. And this is used for making measurements in, irregular shaped objects. As you can tell, you see the 2 pins inside a pocket of a tray. So, how do we make our packaging measurements? Well, first of all, we want to place the packaging material on an insulated support surface. We want to place the test electrodes of our integrated checker or meter near the center of the package, if we're using that integrated checker. If we're using a concentric ring probe, again, we place it near the center of the package or on worn areas. If we're using the 2-point probe, again, near the center of the package or in worn areas, and then you can also place the probe into recessed areas as needed. Apply either the 10 or 100 volt test voltage, wait for your reading to stabilize. And again, if you're testing bags, you want to test both the inside and the outside surfaces because they may not be the same. So the pass value resistance is specified in S541. There may be some user-specified requirements, but the general resistance range for packaging materials is 10 to the 4th ohms to 10 to the 11th ohms. We don't like to see packaging materials less than 10 to the 4th ohms because there is the possibility of damaging product by contact with a low resistance. So if you were to put a charged product into a low resistance bag, you would have the possibility of causing damage to that product. So the general resistance range, 10 to the 4th to 10 to the 11th ohms. And finally,
Arnie,
yes,
before
Ted,
you
please.
move on, we have a question about the concentric ring. And the question is, why does it matter if the center or the outside ring is the sensing contact?
That's a good question. It has to do with the design. Basically, if you use the center as the measurement electrode, the measurement point, then you sort of have a little, isolation because the outside ring is grounded. But I haven't seen that it makes a significant difference here unless you're measuring very high resistance materials. If your resistance measurements are all up in the 10th to the 11th ohms, then which way you connect up the electrode could make a difference. But if you're measuring lower resistances than the 10th to the 9th ohms, I don't think you'll see any difference between which way you connect up the electrode. Ted, do you have any other information on that?
No, I think you're right. I've had the same experience.
Mm-hmm.
There was a question here too. I may have missed it earlier. Any standard length for the drag chain to contact the floor?
Well, you're asking someone that really doesn't think drag chains are really the way to go here. But I would say if I were using a drag chain, I would really like to see about a foot of the chain in contact with the floor, because very often I've seen drag chains that were so short that only 1 or 2 links of the chain actually made contact with the floor, and they got dirty really quickly. So I would say, if you have to use a drag chain, you have no alternative, that try and get at least a foot of chain in contact with the floor.
If I can add to that, Arnie,
Sure.
One of the difficulties, of course, with a drag chain is, like Arnie said, you need enough of the chain on the floor, but then you end up with trip hazards if you've got chains hanging out from under things. One strategy that I've seen is if you've got a cart, have a chain attached to one corner and then go across diagonally and come up and attach to the opposite corner so that you have the full length of the chain on the floor. That can help. We've also seen where you've got one going diagonally from both corners with a heavy round washer in the middle, so you are making contact. Well, back when I worked at Motorola, I had a technician that worked for me that had a little tassel of chains in the middle of a cart, so there was always something touching. It can be done. The problem is when you've got links of a chain, they don't always stay connected to each other. They're kind of loose. And so you need, and like Arnie said, they can get dust bunnies and dirt in there. And if you only have a few points of contact, a lot of times people use tape on the floor to designate where things go, and you could land with the chain on the insulating tape. So there's a lot of things to keep in mind. It's generally preferable to use ESD control casters or wheels. So then you have 4 points touching, or at least 2 points that would be touching. So, and when you order the carts, it's not that much of an expense to get the wheels. I hope that helps with the question. Don, do you have any other comments on that? Evidently not. We're not big proponents of the drag chain. Sometimes customers do kind of like to see them. It's better to use the wheels if you want to add a chain for visual purposes. That's your purpose. There was also a couple other questions, Arnie. I don't know if you can see them in the chat. Jim Aveski has a question about different kinds of ionizers, whether there'd be any benefits for compliance verification if you had one that would display the ion balance or alarm or turn off when it's out of balance. I don't know if you want to spend some time here or at the end discussing that.
Well, I can answer that one quickly. You know, ionizers come with lots of features. And of course, all the features cost money. So at some point you decide what are the most important features to have, and you can buy them. However, any type of on ionizer, you know, display of balance doesn't meet the requirements of TR53. TR3 is very specific about how the ionizer should be measured. And there's no mechanism for replacing that measurement with something that is a display on the ionizer itself. So it's nice to have those displays, and it's good to have alarms. You know, if the ionizer is not working, it should turn itself off. However, as far as auditing and TR53 compliance, those won't make those don't meet the requirements. You really need to use the instruments that are specified in SP 3.3 and TR53 to make measurements of ionizers.
Thank you, Arnie. That's good. There's another question about the concentric ring. Does it matter if the center or the outside ring is the sense?
Okay, well, we did talk about that already.
Okay. And then Harry was wondering if you should condition packaging materials first to under 12% RH. And generally, Harry, that's done when you're qualifying materials. If you're doing compliance verification, you check it at whatever the ambient humidity is.
Mm-hmm. And that's true for all the ESD control materials. The qualification process is different than the TR53 verification process.
Oh, and Diana was highlighting that I think she means in relationship to drag chains, especially concerning in areas that don't have conductive floors throughout the facility. Yes, of course, drag chains wouldn't work very well there.
Wouldn't work. Those are the cases where you need to have some kind of ground cord on your mobile cart so that you can, you know, connect it to ground when it gets where it's going.
So Ryan said he may want to review this presentation again if it's recorded, and wondered if it'll be emailed to the group. Ryan, I think it's going to be posted on the Dangelmayer website where you can find it. Is that accurate, Ted?
Yes, it is.
Rather than clog up your email, you know?
Yeah, I would expect it would be there either later this week or next week.
Mm-hmm.
That's all the questions at the moment.
Okay, so moving along, the last item we're going to talk about is the process required insulators. And your objective is to verify that if you have process required insulators, that they don't exceed a maximum field strength. The references for the ESD TR 2020 handbook. And note that non-essential insulators, those are different than process essential insulators. Non-essential insulators should just be removed from the process environment. Get them out of there. No styrofoam cups, no sweaters, anything that's not essential to the process and an insulator should be removed from the process environment from the EPA. Our instruments for checking the insulators are first our field meter. It's an instrument that measures the static charge, the field from the static charge on materials, and our electrostatic voltmeter. It's also a sensing instrument used to measure the surface potential resulting from the static charge on materials. Now, why do we have two instruments? Mainly size. The viewing area of the field meter, you hold it 1 inch away from the surface of the object you're measuring, and it measures the static charge or the field resulting from the static charge in a 4-inch diameter area. So it's measuring everything that's in there. Now, if you have opposite charges in that area, it might measure 0 even. And you may, you know, it's good to move it around to make sure that that isn't the case. But also, if you have a small object and you try to measure it with a field meter, what you're measuring is not only the field coming from that small object, but you're also measuring everything else within that 4-inch diameter area. And there might be ground in that area, and it might give you a measurement that's lower than the actual measurement on the object. So We use the electrostatic voltmeter in those situations. It's used for measuring small objects. Because it can be held as close as 1/10 of an inch from the object you're measuring, the area that it's looking at might be as small as 1/2 an inch. So it's capable of making measurements on much smaller objects. So if the object is large, use an electrostatic field meter. If it's small, an electrostatic voltmeter is the preferred measurement instrument. So how do we make the measurement? Well, first of all, we turn it on. It's always a good thing to do. Then we make sure that the meter is grounded. To make accurate measurements of fields, your meter must be grounded. You want to zero the meter, make sure that when you're looking at ground, the meter actually reads 0. And then you position that meter the specified distance from the object. If it's a field meter, 1 inch. If it's a voltmeter, as close as 1/10 of an inch. You want to allow the meter to stabilize, and your reading will be either in volts per inch or volts. Record the meter reading. Now, what are the requirements? Now, here's where we get into some problems. I'm going to give you the S2020 requirements, and then I'm going to give you a better idea. Okay? So, for any object that is greater than 1.25 inches from your ESD sensitive objects and less than 12 inches away, the pass value shall be less than 2000 volts for each object. So if the object is between 1.25 inches and 12 inches, it can have up to 2000 volts on it. Okay? Now, if the distance to the object is less than 1.25 inches, then the pass value is less than 125 volts for each object. Okay? Now, here's the problem. According to this, if I have something at 1.3 inches, it's okay to be 1,999 volts. Okay? At 1.3 inches. But at 1.2 inches, it can't be more than 125 volts. Does that make sense? I don't think so. And besides, those of you who have had experience with charging objects, with triboelectric charging, you never get the same charge on the object 2 times in a row. So any object that charges, whatever you measure on it today, it's going to be different tomorrow. And Murphy's Law says that whatever you measure today, it's going to be bigger tomorrow. So in general, our recommendation as best practices, not for S2020 passing, is that if an object charges at all to any value, keep it at least 12 inches away from your ESD sensitive products. You always will be safe if you do that. The specifications in S2020 can vary quite a bit. The results of your measurement will be different every time you make it. And the only way to be sure that your process required insulators are not going to present a hazard to your product is to keep those process required insulators at least 12 inches away, or you've got to have ionizers there to reduce the charge on these objects. Because remember, what is the most critical process required insulator? It's usually the product itself. And there's no way to separate that by 12 inches or any distance if it gets charged. So you not only going to protect from process required insulators by distance, but you also need to have ionizers there to make sure that the insulators you can't separate by distance will have the voltage on them neutralized by the ionizer. Okay, one more thing we need to talk about, and that is, how often do you do the auditing? The compliance verification objective is to identify significant changes in the ESD equipment and materials performance over time. That's why you're doing compliance verification, to verify that once you have working ESD control materials, they continue to work as expected them to. So you need to set the test frequency based on a number of things. First of all, on the critical nature of your ESD sensitive items. How sensitive are they? How easy is it for them to be damaged? And then if you're using ESD protective equipment and materials, what is the risk of failure of these materials? They all wear out with time. Your ionizers will develop problems over time. Your work surface materials will not meet resistance measurements after a long period of time. Your wrist straps may fail over time. How often you test these things will be determined upon what your failure rates are and the critical nature of your ESD sensitive items. So here are some ideas about test frequencies. Daily wrist strap checks may be sufficient. You check them once a day, that may be enough. Better would be constant wrist strap monitoring, that you might need to have those wrist straps monitored and make sure that they're always working. Wrist strap monitors often have a way to monitor the work surface mats as well. So they will, having this type of monitoring in place means you don't have to check those items as often as you might otherwise. Your packaging checks will depend on the composition of the packaging and its use. Some packaging loses its ESD properties with time. So you need to periodically check not only the packaging that's out in the work area, but also the packaging that's in the storeroom. Because if it stays there too long, it'll lose its ESD properties. Some packaging is humidity dependent. It won't work at very low humidities. Some packaging has a limited shelf life. It loses its ESD control properties. And some materials, such as floor finishes, may require more frequent monitoring because of their lack of permanency. They're not designed to be permanent. Or some materials, such as ESD vinyl flooring, may require less monitoring. So you have to look at all of your ESD control methods and decide, based on the critical nature of your process, how often they need to be monitored. Typically, we think of either 1 month or 3 month intervals should be sufficient, but when you start collecting data, you'll be able to determine whether your test frequency is often enough. If you go out there and do your monitoring and find everything is working, you're probably monitoring too soon. You could increase the test frequency there. If you go out and do an audit and you find a lot of things are not working, that really does indicate you need to be doing the audit more frequently. So there are startups 1 to 3 months, and then analyze the data to see if you need to check your system more often than that 1 to 3 month interval. So our conclusions here: first of all, auditing is essential to the success of any ESD control program. Set it and forget it doesn't work for ESD control. You've got to go back periodically and make sure that your ESD control methods are working. The TR53 compliance verification standard is synchronized with the requirements of ANSI ESD S2020. So the worldwide static control document S2020, TR53 as its companion, tells you how to do the compliance verification needed for the S2020 standard. All elements of your ESD control program will need to periodically demonstrate compliance with the facility requirements. You've got to check them periodically. And that failing a compliance verification test requires troubleshooting and corrective action. Now, it will depend upon your company as to whether your auditor does anything other than auditing. In general, your auditor just says, this is not working, it needs to be fixed. Someone else needs to come along and do troubleshooting and corrective action. The troubleshooting will often use the same instruments that are used during the compliance verification. So the skill of the auditor might be useful in troubleshooting, but corrective action may not be the job of the auditor. That may be someone else's job to fix whatever has been determined is not working. So that's all I've got today. We're at slide 42 of 41 slides, so that means it must be over by now. And if there are any more questions, I'm happy to take them.
Arnie, there were a couple of questions that came up along the way. I'm not sure if they got answered already.
Okay.
Richard was wondering if a field meter, he said, I thought that the field meter was only good for large areas, and he is correct. It should be bigger than a 4-inch diameter.
Right.
Um,
You can measure smaller things with the field meters. No question you can measure them, but the measurement may not be accurate.
You have to be aware of what else is is nearby that could be influencing the field meter, because it takes an average of what it sees in a 4-inch area. And
Mhm.
even when I only had a field meter and would suspend a small item in space, the space part was also averaged into that reading. So if I could
Mhm.
get a reading on that item, it's not actually just what was on that item, but what
Right.
the meter saw in a 4-inch diameter.
Mhm.
There was
Yeah, and if you're measuring small objects with a field meter, you can be pretty sure that the field coming off that small object is greater than your actual measurement.
Yes. Now there was a question about I imagine it's another meter, because it said this meter shows 350 volts, never can read below 10 volts since it says 0.00 kV. And that David had this question. I'm not sure if it was relationship to one of the slides. Do you want to ask that question further, David? It may have been covered somewhat in the rest of the
Mhm.
materials. I know we cover these things in depth during our TR53 certification. So
I do
might
think
be,
his observation is valid that you can't,
Yeah.
you
Um,
limit.
There are, field meters out there that the least significant digit is 1 volt, and there are others that the least significant digit is 10 volts. If you're measuring, just the field from objects, either one of them will work fine. The advantage of having the 1 volt least significant digit is that you can make measurements of ionizer balance more accurately.
so
It might
Arnie, there
also
was,
relate to the switch that changes it from kilovolts to volts.
Yeah, that's exactly what it does. It changes it from a 20 kV maximum with a 10 volt least significant digit, and it's changed to a 2000 volt maximum with a 1 volt least significant digit.
so there was also a question, which maybe there was a typo on the slide, I'm not sure, but Diana said, did the 2020 indication change? I have 125 volts at 1 inch rather than the 1.25 inches that Arnie mentioned.
Good. Someone caught the typo. It is a typo. It should be 1 inch.
Well, we need to have Diana be one of our proofreaders, I think.
Exactly. No matter how many times I go through slide sets, we always find a typo, another
Yeah,
typo.
just to clarify, I think she's suggesting that we were talking about 1.25 volts rather than 125 volts.
No, it's
It may have been
125 volts at 1 inch.
It's 125 is correct.
Mhm.
Yeah,
1 inch.
but evidently it said 1.25
Right.
inches somewhere. So we'll have to go back and look at the slide. Or Arnie said that.
Yes.
But see there, Ted, it's a
This should be 1
typo.
inch.
And we have fixed this before, but somehow when we go to find our slide deck, we don't always get the most current one. So thank
Mhm.
you, Diana, for catching it. And it's in
Absolutely
the
correct.
in
Should
the
be
one
1 inch.
below also. We shouldn't have 1.25 inches. It should just be 1 inch.
1.0.
Yeah, it's interesting. How many times have we seen that?
How many times have we not seen it?
How many times?
Yeah, that's a good way of putting it. Let's see, any other questions? I don't see any. We have another minute. If somebody has another question, feel free, but
Well, David
Arnie,
did say that he got his question answered a few slides ago, so that's good. All right.
and thank you, Arnie and Ginger both. As usual, you did a great job. And the comments are coming in like that now too. Thanks,
Yeah.
Jeff. Well done.
Yeah, thank everyone for joining us, especially the
My
people
pleasure.
that just had, several days of ESD out in Tucson. You obviously can't get enough. You're just like us.
So true.
Okay. Thank you to everybody. And
Thanks, everybody.
Yep, great.
Hope to see some of you at the certification class where we can go into great depth and we can all take turns telling Ted what to do.
Mhm.
Yeah, Ginger really enjoys that. Thank you.
Okay,